Okay. Like you said, my talk's on TMTO and why. So this is time memory trade-offs. You have chain tables. The original ones, the classical Hellman tables. Then there were distinguished points. Then in 2003, there was rainbow tables. This made the time memory trade-off better. So when we're talking about time memory trade-offs, there is no faster or smaller because each one of these are adjustable. So if you say, oh, this time memory trade-off is faster, well, you could make a rainbow table, larger, so then it would be faster, or this one's smaller, because in the history there's been, the ones below, rainbow DP, chain distinguished point, VDP, rainbow VDP. These were all made after rainbow tables, but they didn't focus. Basically, you could make an optimal rainbow table, either smaller or faster, well, and both. So so the problem with rainbow tables is they take a while. So if what you need to do is extremely time sensitive, you would want something that does it instantly. This is like 100 milliseconds or something. So if you're cracking brain wallets, basically you want to crack the password before anyone else does, so that you can transfer the money to, if you're an asshole. I have not actually done this. I should probably mention. Anyways, so there's hash tables that do this, and then there was a talk at BloomCon, Bloom Reverse. So these all are constant time. And so for every password you have in your table, you have to store some amount of data. So I should probably go over what big O notation is. Is everyone familiar with big O notation? No, probably not. So big O notation 1, that means constant time. So anyways, with rainbow tables, for every password that you store in a rainbow table, you only need to store roughly n to the 2/3 amount of data. So if you have a billion passwords, you only have to store 1 million amounts of memory. And then when you actually need to use it, it costs 1 million. Then there was another thing. Someone just liked the name rainbow tables. So even though it actually takes n amount of time to use it, what they did was you had to do PBKDF2, and then you got a network key, and then you had to use that to check to see if the handshake was actually valid. And so the PBKDF2 takes a lot of time, so you just do that, and then you have the network key, so then you can do a couple hash functions, and then you get to check it. So it increases the speed by a factor of like 1,000 or something. So optimal rainbow tables. This assumes that you have as much time as you want to actually build these. So a perfect rainbow table is where there's so you have a start point and an end point. The start point is just like a starting password, and then you do this, you hash it, and then you basically a reduction function. What this is a deterministic random password generator from the key space. So you do password, then you hash it, and then the hash gets turned into another password from the key space, and then you hash that and continue. Then you have an endpoint. The endpoints will actually collide. You'll have different start points, but the endpoint will be the same for multiple. When you perfect a rainbow table, you remove all the duplicates. So you want sequential start points, because if you were to do random, let's say the key space is 2 to the 50. If you did random, you would need to store 50 bits. But if you did sequentially, you would need, well, 2/3 of that. Anyways, then minimal perfect hash functions. It's a way to basically cost a couple bits, and that gives you an exact endpoint. So, well, it gives you the exact row that you need. So you have your start point, and then you add a couple bits for the collisions to check for it. Anyways, so then there's floating point modulo. What you do is you basically pre-compute the inverse of what you're trying, and you multiply. Anyways, then stop generation checkpoints. So cat photo. So key space. Anyways, so this is you have to have a fixed key space before you even start any of these, whether it's rainbow tables or hash tables. So this, if you're doing, if you're trying to crack encryption like DES, your key space would be all the keys that are possible, so 2 to 56. Or if you're doing passwords, you can have a dictionary and then mangling rules. So you would just, your key space would be how many dictionary words you have times how many mangling rules you have. And you can also do like mask attacks, like brute force and stuff like that. So when you're doing so this is really just for reference, the formulas. They're very simple. Well, it's, you just, anyways. So when you're doing a lossy hash table, you don't want to store the actual password, because that takes a lot of space. What you want to do is so each password has a number associated with it. So like if you're brute forcing 4 letters, AAA through ZZZ, the first one would be AAA, so 0, and then AAB would be 1, all the way to anyways. It's like 600,000 or something. So this is how you would convert from the password ID to a range ID, and then a range ID to the specific password IDs for the range. Then you would just brute force those. So basically, the obvious way to do this is just store a key value pair in a database. Then there's basically ways to index it. So you have prefix index, where there's like a very simple one, index, integer prefix index. Basically, you just have a fixed number, and that tells you how many. So you take a prefix of it. Actually, my next slide is this. Sorry. Anyways, and then there's minimal perfect hash functions, and then there's this Bloom reverse. Bloom reverse was, like I said, it was BloomCon, which has nothing to do with Bloom filters. But the optimization for that was, so for every password that you have in there, the optimal setting would be to use, you had to use 1.44 bits per entry. well, per password times how many times you actually do lookups into it. So every lookup that you did into it would cut the key space in half. So to cut the key space in half, you had to use store 1.44 bits for every password. But if you were to do a key value pair, you have an index which costs some amount of space, plus you have the password range. Every bit you add to that decreases the key space by half. So Bloom reverse would be less efficient if you were trying to do this. Anyways, so very simple, just MD5 password, and then a prefix index would just take the first 16 bits, and then you would have the passwords. So so with the Lossy hash table, you would just actually get rid of the rest of the hash. You don't actually have to store that because you're going to brute force password range. Well, in this case, you would just have a password. And then you would be able to know whether or not you actually cracked the password. So you would group it by the same prefixes. So you'd store, so you basically just have a pointer into a list at these positions so that you would know where, like how many passwords were in each bucket. So if you were to do integer prefix index, you would just take the prefix, and then you would, so in this case, what you want to do is store 16 bytes of data. Well, each chunk is 16 bytes. The first 8 bytes are an exact offset into your prefix and sorry. Anyway, so the 64-bit number that is basically a pointer into your array of passwords, like this, the password range ID. So each one of these things represents 4 actual buckets. So so you have an exact offset into it, and then you have 4 counters of how big each bucket is, so that the first bucket would be hex 8. So there would be 8 values in there that were like that. Yeah. Then the second bucket has 6, and the third one has 10, and the fourth one has 10. So if you were going for the second bucket, you would just add 8. Yeah. So if you're looking for the second bucket, you would go to address 0, which is here. Then you would add 8, which then you would start here, and then you would go for 6 to there. So that would be your range that you would need. You would have to go through. You can actually, since they're completely sorted, you can do a binary search within that data set. So instead of brute forcing all those ranges, all 6, you would only have to do log base 2 of 6. So 3-ish. Anyways, so I had technical slides, more technical slides, yeah, sorry. Then I was going through it and I was like, wow, this is really not useful. So, it would only be useful for, if you were gonna be, implementing this exactly. So I'm just gonna go over what Elias Fano is. It's, you would, so Elias Fano is actually used to represent a sorted list of numbers. What I'm doing is, so basically the pointers to each bucket, those are the sorted list of numbers. So I'm just representing those in Elias Fano, which is just an encoding. It's more efficient than doing integer prefix index. One more note on this. This is if you were going to do 32 bits per prefix index on average. It's 16. So each one of these is 16 bytes divided by 4. That gives you 4 bytes. What you can do is if you shrink the pointer to 48 bits, then you have room for 16 5-bit numbers to represent the bucket size. When you do that, you have to make sure that each bucket is obviously smaller than 32, but each bucket has less than 32. But when your index is that small, you can make the buckets really small. It's just yeah. So minimal perfect hash function. So it's like a hash function. So minimal means that your array is the exact same size as the amount of data that you're storing. Perfect means that there's no collisions in it. So there's this algorithm called compress, hash, and displace. So it costs, well, you can adjust the amount of cost, but for 2.3 bits per password, you can, it gives you an exact range. So exactly one password range ID that so you only have to brute force that one range. But it's a little slow to generate these. So it's 400,000 per second to build the minimal perfect hash function. That's on a quad core. Anyways, Hoffman encoding. With this, basically you do the same exact thing as a prefix index. And what you do is you actually encode the bucket sizes with Hoffman encoding. Basically, with Hoffman, it's the more buckets that are the same size, the smaller the code word for it is. So if you have a lot of buckets that are all have 5 things in it, it's going to be like a bit or 2 to represent that one bucket. But less common bucket sizes, those would be larger. So this is funny. I was trying to log into I have this. Actually, I probably should have this. I made a Lossy hash calculator. Basically, it does all the math for you and whatnot. I finished it a while ago, but I was like, I changed all the style sheets on my website, and I needed to do diff, and I was gonna do it before I left, but I was like, oh, well, I should do it at least now, and Google doesn't think I'm me. So I will get that up, well, I guess when I go home. Anyways, examples of this in the real world. So brain wallet cracking. Ryan C., he did a talk earlier. He actually observed people. He would put bitcoins, not money, bitcoins into a wallet, and then he would notice that it would be removed really fast. So someone either would need a lot of GPUs or computing power to go through the key space continually on every new brain wallet every new Bitcoin address and then crack it that way, or they needed to do some sort of time memory trade-off so that they could do a bunch of work beforehand and then crack them really fast. Nitrogen. So he has I don't have his website on here. Anyways, so what he did was he used a prefix, integer prefix index to generate one of these tables for MD5. He has 1.1 trillion passwords in it. So he went with a little less efficient method, just so that it would be really easy to write. So he got around 5 bytes per password. And then there's this website, CMD5. They say, so they have a Chinese version, an English version, and a Russian version. And all the numbers, when you translate what they say, they're all different. So, but the largest one is 24 trillion, and they say they have 160 terabytes of disk. So that's 6.67 password bytes per password, which is less efficient. So optimal settings for this. Can you see that? So this is a screenshot of the Lossy hash calculator that I wrote. Basically, you put in all the settings. There's actually full auto, so it just does everything for you. The most efficient one, so I standardized them all to the same size. And so the one that's the fastest is Hoffman Encoded. And then it's minimal perfect hash functions, and then Elias Fano, and then 8-bit prefix indexes. That's the 48 bits for the pointer, and then 16 5-bit pointers. And then Bloom reverse is last. So the first 4, they're all under 100 milliseconds. And then Bloom reverse is if it was the same exact size. So it would be like 2 to 3 seconds. That's what another thing for time memory trade-offs. Most password crackers don't actually use, well, none really, use rainbow tables. The only real uses for them now are for like encryption. Several years back, there was the A5/1 rainbow tables. And then actually there was a talk yesterday, Think Complex Passwords Will Save You, which they actually built a rainbow table to crack DES specifically for MS Chap v1, because you can set the salt to a specific value. And then, because all these time memory trade-offs fail if there's any salt. So unless the salt is fixed, like admin or administrator or whatever, or in the case of MS Chap v1, where you can just set it to something. For the efficiency of Hoffman encoding so the index itself is 1.8 bits per password. And so the best that you could ever hope for would be 0. So basically, you need less than 2 bits, and then for every bit that you add, divides the key space in half. Holy crap. Questions? I think that would be all my technical slides. Made it longer. Yeah. Sure.
So you mentioned you were locked out of your account. I'd be interested in looking at this in a passive thing where I can look at it. Well, does that mean that you were going to post it later? And if so, could you give the URL? Because I think the work that you're doing was very interesting, but I had a little trouble following your talk, so it'd be great to have some follow-up material.
Tobtu.com / so it's tobtu.com. That's my website, and then / LHT.
Wait, I'm not going to get that. Could you?
Yeah. Hey, I'll edit my slides live.
Thanks.
I will. You know what's funny? In the speaker room, we were actually talking about this. So that's the Lossy hash table calculator. There's also a rainbow table calculator. Huh?
This is pair slide editing. We're good.
Pair slide editing. Nice. Oh, actually, so I didn't actually mention this. So I did this like 5 years ago, and I was like, oh, I'll finish it, next week. And so I never actually got around to finishing it. It has it's actually it has like formulas, info on rainbow tables, the different types of rainbow tables, stuff like that. The Lossy hash tables. Oh. Hey.
Okay, thank you very much. That was really, really interesting, very technical. So thank you.